And nothing is happening yet. No. All right. So I guess, well, we are not that many. Actually, there should be like 15 people. And I'm not sharing now the screen. There again. And I'll take the full screen. Should we still wait a couple of minutes more?
Yeah, I think so.
Yeah?
Wait a few minutes.
I think so. Wait a little bit. Yeah.
Yeah, okay. Okay. Okay, let's see. No, it doesn't seem anybody new is joining. Okay, what do you suggest? I suggest we start, and then maybe, Paul, you can just help with admitting people to the webinar.
Yeah, I will do that, but I thought you said that we had something like 10, 15 people that...
Yeah, who accepted the invite or who received the invitation, but...
I see a few that haven't joined yet, but...
Yeah, I know I got this morning, I got one declination, but I don't know, maybe normally people, you know, join the webinars when they can, so to say. Yeah. So how many do we have right now?
We have only 2 guests.
Only 2 guests, okay. And time is 5 past, yeah. It's a bit hard to say. Okay, there's someone joining now. Olivier, could I ask you to go on mute maybe? Because I think we hear either you or someone else.
Yes,
Thank
sorry
you.
about that.
No worries. Okay, I suggest we start.
Okay.
And let's just see if people drop in.
Yes.
So welcome to the webinar this morning. And I have to just shift my screen. So, which is about introduction to additive manufacturing using metal to the area of consumer products, machinery, and architecture. And we are a team who works, a few of us who are here today work in the project. The project is funded by the EU Horizon 2020 Research and Innovation Program. And we are, I think, right now on the almost 3rd year. Yeah. So shortly, briefly, the agenda today. We will hear, well, mainly Lars will present, introduce the project and the possibilities that the project offers. Then we have a part that Emmanuel from CSEM from Switzerland will present some real cases where we are, that we have in the project, but it's more real than a lot of theory. Then we don't have Edward, but Lars will take that part of benefits of additive manufacturing, some unique selling points, examples also from the sectors that we cover here right now. And the last presentation will be from Paul, information about the open call that we have in the project, different offerings for the companies and organizations. And at the end, we should have time for some discussion, questions, and open points, and so on. So the aim of the webinar is pretty much to introduce the additive manufacturing possibilities for the area of consumer products, machinery, and architecture through the EU project MANUELA, and also to present you the offerings for the companies via the open calls or the open call. Okay, so if we start with Lars, shortly introduce the introduction to the project, MANUELA project.
Mhm.
So Lars, please just tell me when I should change the pages.
Okay, I'm here. So you're going to use that type of presentation mode. I'll just make it toggle this full screen. Okay, so everyone, welcome. My name is Lars Nyborg. I'm the overall coordinator of MANUELA. Perhaps you see me sitting here in one of the small boxes here, my face and so on. I'm happy to share a little bit short information on MANUELA. What you see here, the slide you have in front of you now is the consortium. So this is one of the biggest projects across Europe in development of powder-based additive manufacturing, where we work with basically two technologies. I will come back to that. There are a lot of solution providers. Also, we have a number of companies already involved, as what we have done is to work with some kind of predefined use cases, which I think you will hear a little bit indication about later on, so you get a little bit glance of what is happening and ongoing and capacities that are built up. Next slide, please. When we look on benefits of AM, we talk normally about its innovative, flexible product design that we can create complex geometries. And probably you have seen that around that this is one of the potential benefits of additive manufacturing. If we do it in a proper way, we can then bring the material utilization to a very high degree, basically mean that we will reduce waste generation quite a lot, and hence it can be connected to energy cost savings. It could be really something that we have to take advantage of when it comes to the product development or the overall the develop of new products and manufacturing that will reduce lead times. And of course, often is like this, that we consider the technology that you can have different variants without needing tools, etc. for manufacturing. Hence, there is enhanced product differentiation capabilities by this type of technology. So please, next slide. So there are some key innovations in MANUELA. We're working quite a lot with tailored recycled metal powder. We do develop, but not only physical sort of solution, but also dashboard, the whole digital solution. We work a lot with the workflow optimization automation. That means that going in the real on the industrialization scope, this needs to be in place. We also have a lot of activities that are connected to what we call real-time process monitoring, basically on the edge implementing the coming AI and ML solutions into the manufacturing capabilities. And of course, contribution to qualification and certification standards. There are a number of offerings there, and that of course could be pre-industrial testing. The full manufacturing chain is available across Europe, some kind of one-stop shop capabilities, go first time right, going into products with new segments. A lot of knowledge, which I think is something that is not common if you go to normal service providers, about materials integration into the manufacturing line. Of course, green technologies, the guidelines, and also, as Anne indicated, the quality control on quite advanced level. Next slide, please. how the service is going to be then running or is running and developed is that we have a software layer, as I talked about. I'm going to go into details about this, but this means that the entrance to this is going to come directly into the design capabilities, and we have the software layer, and in parallel we have a hardware layer where the hardware layer is all the sort of connectivities to the material flow in the machineries in different size, the post AM capabilities, and outcome here is that there is a lot of work also on automation and interaction between the different stages. And then, of course, the full line optimization, enhanced at the end qualification and standardization. So I have to understand that there are two things, a physical flow and a digital sort of dashboard in the bottom, right? Yeah. Next slide, please. As what we are creating is a single entry point. That's why Caroline and Paul are here. They are acting as the entry point. That means Chalmers Industriteknik, which is an independent institute working with Chalmers University Technology, is and will have the front activities for the pilot line. And they can act as neutral board, will not need to carry the infrastructure and work initial as a project office, and can also be the one that form agreements with the nodes and others. And that's the key point. So the idea here is the client can get in contact with CIT at the first one-stop connectivity, and CIT has then the links into the sort of solution providers within the MANUELA concept. This is how we built it. Next slide, please. So, and of course, there's design flow, design optimization, process simulation, and there's a qualified testing, analysis, and getting data once you have built test samples and all your parts also. Next slide, please. I think it's important here to understand that there is extensive work here, and I think Olivier and Emmanuel and others can testify here that we are actually more or less in having a solution for a digital dashboard in place today, with the potential different elements of such dashboard where we talk about these type of concepts like digital thread, the digital twins, etc., for different parts of the process. So that's a very important part of the development and capabilities MANUELA. So you can think about that at the end, going from a product idea to a realization can be done quite a lot along a digital chain until it's ready for going into the hardware layer and realize the product. Next slide, please. Some kind of capabilities, a lot of resources at Chalmers. I don't go in detail this, but we have a number of printers. Next slide. We have a number of printers at Polito, which is another site. You see it's very much connected to laser powder bed fusion. That was at Chalmers also. Take the next slide. And we have other resources at Polito. We have possible making powder, another post-processing like hot aesthetic pressing, number of ovens. And there are also, of course, a lot of polymer-based AM systems that was in the other sites here, which is something that we can do in the beginning for prototyping before going into sort of the real manufacturing, the metal printers. Please, next slide. And at Erlangen University, FAU, we have also a number of printers. Their scope is to work with another technology called EBM, where you use the electron beam as the technology for building materials, whereas Polito and Chalmers are working heavily with the laser-based processes in the powder bed. Next slide, please. And that, of course, is not just the manufacturing equipment. We have the whole facilities of a lot of characterization that is needed for qualification, both in the lab materials characterization, but also powder characterization. I don't go into the details here, but you can get this type of information through having access to the slides here. Please, next slide. And RISE IVF is also a part of this. They have a special role in the post AM processing, but they have also capabilities in printing here can be added. They have so we have quite big sort of capabilities in doing prints in a number of different sizes, different technologies, to link to the sort of contact node that is supposed to be built through CIT. Next slide, please.
Yeah, that was your part, Lars.
So that was my part. So this is just I was quick now because I did not go into details, because I think the interesting is to drill down to what really can be achieved, the use cases. This can be shared to everyone, this information. This is public information. So it shows the scope, the thoughts, the capabilities that are there across Europe. Remember, across Europe. It's not in one country, it's across Europe. So thank you very much.
Thank you, Lars. So now we have Emmanuel, who will present a bit more around design, but also I think 2 use cases that we have in the project, right?
Yeah. So
should I change the pages or? Yep.
Yes, please.
Okay.
Yes, so mostly I will present which software tools are now available in MANUELA. What is the design flow we use to design or update an existing design to be printed on the MANUELA pilot line? And I will show briefly what optimization can bring, and I will show a use case example. So go ahead, Carolina.
Yes.
So the design tools, so as Lars mentioned, we have what we call the dashboard. So the dashboard covers the full development process. Maybe I will cover the full development process. So we start with the part requirements. So the one that wants to manufacture a part will give us some requirements on the part, so the size, material, do we need post-processing, and so on. Which norms should be followed. We analyze the design. We see if it can be manufactured on the pilot line or not. If not, we may propose an alternative, so adapt a bit the design, propose alternative materials. Once we find an agreement with the use case owner, we start the design optimization, so using a tool called Apex Generative Design. So here at the bottom.
If you can point at the presentation, or?
No, I cannot point.
No?
No, as it is on your PC.
Yeah, but I think on this screen you can. Okay, but you are on the.
Yes.
Here, I don't know if can you see me pointing? No?
Yes. So yes, I can see your pointer, Carolina.
Okay.
Then we process. So then we simulate the process using Simufact. So we see how the part will build. We can see various deformation. So at that stage, we do several loops until we meet the requirements. And then once we are ready with the procurement specification, we start the manufacturing and post-processing process. And everything runs in closed loop. So we are so the pilot line is monitored. So we collect data on the machine. We have a big collection on data, and some of our partners, thanks to machine learning, adapt the machine parameters to have to continuously adapt the manufacturing process, And at the end, we compare what was produced with the simulation we perform at an early stage of the process, and we can again adapt the design if necessary. So go ahead, Carolina.
Yes.
So you already have seen this slide, but I will go a bit more in the design flow. So we start with, so for instance, you can see this bracket on the top left-hand side, general architecture. So we start with a general architecture that we have to optimize. We define what we call the boundary conditions. So the areas where the optimization can work. We run Apex generative design, and we end up with, for instance, in that case, a lightweight design having the same mechanical properties than the original part. We simulate the process, and before launching the manufacturing, we manufacture test samples. So in that case, we manufacture some blades, and we tested. So we made some fatigue tests of that sample. We analyze the sample, and we see how we have to correct the process before manufacturing the part. In that case, the bracket was manufactured for a space application, so we had severe norms to respect for the part to be manufactured. So go ahead, Carolina.
Yes.
So I will give two examples of use cases developed for what we call a slip ring. So this is a collector that brings the solar energy that is produced on PV panels mounted on satellites to the satellite. So we have it's like it's a collector. So it's a reverse. It's the opposite of a motor. So we have a rotor that will induce energy in the stator. So at the origin, so you can see the rotor at the bottom part where there is a pencil.
Yep.
Originally, to produce that part, the use case owner, Ruag Aerospace, had to produce something like 50 parts, so slices, and to assemble them part by part. Thanks to additive manufacturing, thanks to a process that was developed and thanks to the pilot line, now the part can be produced in we have only one part to produce. So here on the right hand side, so you can see the samples and one slice of the part that we produced to analyze the part. And we now have also the process to print electrical conductors directly in the part. So there is a big save of time to manufacture such a part. And one big advantage, one advantage of a pilot line, so it will depend, of course, of the use cases, but in that case, we have one of the first machines that can print properly copper. So go ahead, Carolina. So we are manufacturing the rotor, but we also have to manufacture the stator. So the stator is in aluminum. So you can see here the full process again. So we define on the top in the blue part design spaces where we could perform optimization. And thanks to optimization, we ended up with the orange part on the right-hand side. The part now produced is the gray part at the bottom. So we are still optimizing it to try to reduce a number of supports. Post-processing to remove a support for the time being is too time-consuming. And the new generation that will be produced this month has less support. And the blue picture on the right-hand side is to show kind of what we can see when we run Apex generative design. So for this aerospace use case, the main goal was to reduce the number of parts as well as the mass of the part to be produced, as mass equals cost for a space application. Go ahead, Carolina. I think that was it.
Yeah,
Thanks a lot.
Thank you, Emmanuel. Thank you very much. And I think the next part, we are back to Lars, and now it will be a bit different theory regarding different types of additive manufacturing in metals. And then also we have some pictures from different examples of products that can be printed. So Lars, if you'd like to start.
Yes, I'm here. Do you see me? I closed my picture here before when Emmanuel was talking, right? Yeah, which was quite an excellent contribution. I think that was really interesting. Hopefully you enjoyed it, to see how we can bring the benefits of additive manufacturing into a complicated product where there's a lot of stages and assembly, and through this going and creating a product that is one step, one shot capabilities, getting all the designs in place. This is an excellent example where AM is creating benefits. But go back a little bit broader here. For those that are not so knowledgeable in additive manufacturing, we go back to standards. In additive manufacturing whatsoever, if you look on your technologies, there are basically 7 process categories. What's something called binary jetting, direct energy deposition, material extrusion, material jetting, and utility bowl powder bed fusion. This is the technology we talk about here in the context of MANUELA, sheet lamination, photopolymerization. VAT photopolymerization. The last one is basically lithography. Most of these technologies, some of these can only be working for polymers. Some can work with both polymers and metals, but now we are focused on powder bed fusion and as a technology for metal-based manufacturing. Okay, so next slide.
Yes.
And then we look at powder bed fusion. Then, of course, as we said, we are using thermal energy that fuses reaching of a powder bed. And here it's important to understand that even if you talk about metals, there are technologies out there where you can work with polymers or ceramic powder. It is of interest, powder bed fusion, because this is the most grown technique today. And we use a laser or electron beam to melt and fuse. We need a lot of support structures which need to be removed after the fabrication. We may get different properties, different directions since it's a directed build. Typically, there is, in normal cases, some kind of need for post-treatment, heat treatment, in some cases, what we call hot isostatic passing, etc., to relieve residual stresses or perhaps have defect control. But this must be known, these are the one we talk about, but still this is the growing technology.
Yeah, should I take?
Next slide, please.
Yep.
And then we go up to the 2 technologies. This is a little bit the textbook. If we look laser-based powder bed fusion, where we use metal, we use a protective gas. we can have quite large build plates, up to 800, 400, 500 millimeter in X, Y, Z. Quite good range of materials available. We have good capability to reuse the powder, because of course we don't use all powder when we in the product we build. So the technology itself must be built that we are having a good capability of reusing the powder. Roughly fine powder, 2080 micron is used. We can build quite small channels, and then we can actually create decently fine surfaces here. There are instruments out there you can use a number of lasers in parallel that increases productivity, but you can also work to increase the productivity by tuning the printing parameters, for example, increase layer thickness. So that is how the technology is today. Yeah. Next slide.
Yeah.
So if you look on those that are material scientists, key features of materials produced by AM, just want to show this. After we get a fine columnar microstructure built, we can get certain anisotropy in the build direction. But it's important to understand that if we have the processes under control, we typically get densities of well above 99.9 and even better relative density. So people believe in some cases and say, this is material where you have a lot of pores. This is not true. This is hardly at all true. The technology today is such, if we have a processing under control, that we build basically fully dense material. Next slide, please.
Yes.
And that can be shown here. If we just take some examples, do you see, taking just the stainless steel, 316 stainless steel, austenitic stainless steel, well, the typical sort of stainless steel for a lot of application. Here you see through a number of data here: tensile strength, yield strength, elongation to fracture, and impact energy. And you can see that the quite small spread. There is some small difference whether you have it in the argon atmosphere, where you don't tune the oxygen content in the atmosphere, or 820 ppm are when we have controlled lower levels of oxygen in the atmosphere by a special technology that is provided by Linde. And then we have on the other side, if you will work with the generator, uncontrolled nitrogen, or 800 ppm oxygen, 20 ppm oxygen. This is where we work with a nitrogen atmosphere. The other one is with argon atmosphere. But what you see here is that we get very, very good properties. We have tensile strength, ultimate tensile strength in the range of 650, 670 in basically all cases, right? Yeah, which is more similar or better than any wrought material for the established materials processes. If we would take stainless steel, conventional stainless steel, manufacture it in other cases and machining it out, you won't reach these properties. And that's because of the unique microstructure you create during additive manufacturing process. Next slide, please.
Yes.
There are certain things that you get a longer grace, and that in the build direction, and you can get smaller grains close to the surface. Here is a sort of cross views of built materials, different build angles, etc. And you get also some kind of random orientation, depends on how we print it. But the key point here is that that's why the work by MANUELA and others doing a very elaborate sort of design work is important. You need to take care of the design and component, take into account the fact that you have a special manufacturing process, right? Yeah. So the design work here really to take care of the actual sort of specifics of additive manufacturing design is a crucial thing, and that's what we have inside MANUELA. Next slide, please. There is today a number of alloys that are commercial. There is still limited amount of powders that are commercialized. This we should be aware of. But there is also quite a lot of development. There are more materials available when it comes to laser-based powder bed fusion, whereas into electron beam or what is called EBM, a little bit less of sort of commercialized materials. But there is progress and development, and the list can be made longer if you look on all internal developments at different sort of organizations. So next slide, please.
Oh, sorry, there was one more. Yep.
And the other thing that is there as a special capabilities, I'll just show one here with quality assurance. This is implemented in MANUELA, where we have the latest technologies to online monitoring to measure and collect a lot of data inline online. That means that we have a quality control. We can look on the actual melt pools that was created, all the sort of imaging of the layers, layer by layer, and all this information can be stored and connected to the optimization and control of the builds, right? That's key point, right? And the similar system exists inside MANUELA on the EBM processes. Next slide, please.
Yeah.
One of the important aspects, go more into research aspect here, that we have robust powder. Hence, there's a lot of efforts in MANUELA and otherwise to make sure that we control of the powder recycling. This is a key point, and that it is, because with the control of powder recycling, what happens with the powder inside the process and perhaps also the handling process is a specific element how to make sure that you have a high quality build, which is the capabilities of MANUELA also. Next slide. Look on EBM. That's another technology, and I talked a lot about the laser. Now EBM, it must be run in vacuum. It can only be used for metals. Dimensions build plate, you see here. There are quite some robust process materials, and there's been a lot of commercial breakthrough in biomed and aerospace. Certain number of materials are commercial available, but there could be others around there. The technology is like this, that you powder bed pre-sintering. So you use the powder bed as a support. Hence, you use the electron beam to boom, 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 heat the powder bed while and keeping the powder bed at a certain temperature, while you also build the real part inside the powder bed. Hence, support structures, things like that, a little bit different. That means there's a little bit lower recyclability of powder, but of course, since you do this in a different way, you have certain limitation when it comes to design capabilities. For example, creating small channels. So we have to understand, would the product you're interested in would be fit to go for electron beam? Would it be fitted for go for laser? This is the first state decision making. In some cases, you have to do, right? Yeah. The next slide. If you look on different sectors, so go to, for example, the investigation by Roland Berger, and which is found in different brochures. This is the manufacturing readiness level, MRL level, aerospace, tooling, automotive, some years ago, right? Yeah. You can say that it has been more of a breakthrough in tooling, a little less in automotive, quite substantial breakthrough in medical, and somewhere in the mid-range in the aerospace, right? Yeah. And you can see, for example, aerospace, fuel injection, structural elements, blades, perhaps, tooling inserts, tooling business, there is a lot of AM applications today. If it's automotive, of course, short range, or if we go that's really an interesting area, and where there are a lot of things developing. In the medical, there are a lot of this about instruments, hip joints, crowns and copings, etc. So there's a lot of application you can find there for highly sophisticated products done today on commercial basis by additive manufacturing. Next slide. Look at the consumer product. These are some examples, courtesy from different things. I mean, you have this design icon. We talked about that. This is in 18 karat yellow gold, courtesy EOS. EOS is one of the technology providers here. That's quite interesting. So you see, of course, a complicated shape you can create by some kind of design icon here, which is probably very difficult to create by other technologies. But if you look on the examples that the MANU provided, you can understand that AM can really create these kind of solutions. Yeah. Digital metal is another powder-based technology, which is more like the inkjet printing. But you here see some examples, very small products with really good surface finish. So it's a two-step. Then you have another product there, which is coming to courtesy of EOS. And then, of course, going into fashion, you can see here. So it's an interesting leading sector. There are prototypes and models going to fashion. But they're also coming more and more into electronics, where the inkjet and other technology, where the capacitor components, resistor, capacitors, inductors. There's a lot of things happening in this field today connected to additive manufacturing. Next slide, please. Markets. This is an example. If you look on the architecture or things like this, construction area. If you see this, we took it from the web. This is Mexico City Airport, and you see these connectors, and you can understand this if you look on a building, a fancy roof like this in the left bottom corner, and you see that how many of these ones you want, and you see that you can do a very intricate design of stuff here by having these type of connectors. They are perfect in some sense to be manufactured by the additive manufacturing, right? Yeah.
Mm-hmm.
Because they go back to the designs Manu talked about here before in copper, and take in imagination and transfer it to this type of products, right? Yeah.
Yeah.
It's obvious that AM is an enabler for getting products like this in place, right? Yeah. With the flexibility you want to do, right? Yeah. Okay.
Yeah. Should I take the next one?
Another thing is tooling. In tooling, you need tools for injection molding, die casting, tool repair. It could be that if you look on the left hand here you have a tool insert before repair. And then what it is interesting, the fact that the powder bed fusion, there are sort of setups inside the machines today where you can take a piece of a prior product, take away part of the surface and build on top of the part. So you actually do a repair by powder bed fusion. So it's not building the whole product itself, it's seeing where you could cut away the damaged part and have a support for rebuilding something on top of an existing part. That is a possibility actually with the powder bed fusion today. It exists, and the technology like this can be implemented in the MANUELA line, right? Yeah. On the other side here, you have a tool insert injection molding made from MR aging steel, and a tool insert for the die casting. You see here the inserts and then the design capabilities you can have to have improved functionality of the tool. That is something you can create by the design capabilities of additive manufacturing. So you can see a lot of things in tooling do exist today. That means it's not making the product itself, but they're making the facility, the manufacturing of other products in an efficient way. Okay?
Mm-hmm.
Here's another example that you look on tooling. This is something from the tooling where you do work with inserts, and you have the holder here, and you can do it in a design that is completely different from other aspects, right? Yeah. We can take the next slide.
Yeah.
And one of the things we have done, this is just an example from Chalmers, that showing a little bit of innovation capabilities, right here. And we can share this. On the left-hand side, the right-hand side, you see a piece, a product. This is 316 stainless steel. It is going for functional testing now in one place. If you want to build this very tall part with the standard parameters in the machine, it will take you 120 hours. But what we've done here, is that we have developed the process parameter, so we can build the whole piece in 30 hours to full density with equal static mechanical properties, 4 times higher productivity, a little bit worse surface finish, but that is something you can perhaps cope with for the application. So here, what you see here is that this is one of the innovation capacities that we can provide in MANUELA, not just the design, but the productivity. And for an end user, I think it will be a big difference whether the part is built in 120 hours or 30 hours. We talk about 4 times faster built capacity for exactly the same product, and still the product is there and it performs.
Yeah.
Fully dense material, nominally fully dense material. Next slide, please.
Yeah.
And this is another one where we can share. It's a work that's been done between Chalmers, Höganäs, and Volvo. This is a control ring in a normal engineering steel, 4130. So the powder comes from Höganäs AB in Sweden, one of the bigger powder manufacturers, where we have developed a good printability. The material is to full density, is full defect-free, perfect structural component for automotive industry. You see the control ring, it's a courtesy of Volvo cars, the right-hand side here. This is how it looks like when it's manufactured, quite bulky part. And it's fully dense, everything is in place, and it's like it's an engineering steel. The courtesy is here, and you can go back to the work done in our competence center in Chalmers. So here you see also an example of what additive manufacturing can create, right? Yeah, we're talking from going from here in the MANUELA, from powder design, everything to complete finalized print of actual material that was not on the list you saw before. This gives an example of powder development for the process. Yeah. Next slide, please.
Yep. That's it, Lars, for you.
So this, I hope this gave you opportunities and understand about the capabilities. At the end, at least, we were able to share some products that are realized, right? Yeah. And how we can create products in new materials. We can create products with very sophisticated design, bulky products, and we can also work to actually cut manufacturing time substantially compared to the state of the art, right? Yeah, and that lowers cost for the product it in the end, right? Yeah. So thank you very much.
Thank you, Lars. Thank you. All right. So the last presentation part is from Paul about the open call in the project.
Okay.
So I guess I start there. Yeah.
Okay. Thank you. So I am Paul Hägernen, and I work for Chalmers Industriteknik, which is the organization that will interface with the industry that are then interested in working with AM technology for their products. So in the project we have something which we call an open call, and that is an opportunity for industry to actually try out their products or ideas for products that they have that they think that could benefit from additive manufacturing. So this opportunity is available for all countries that are subscribing to Horizon 2020. We will select 10 use cases, which we call business use cases in total. So there is actually plenty opportunity for different companies to be part. Each use case will be funded by MANUELA project to 50%. So it means that the company needs to fund half of the bill that we have for the complete process of design, manufacturing, and post-processing. If you think that you have a good idea for this in your company, you have to apply to be one of the use cases. And you see here on the picture the link where you send in your application. If you have any questions how to make your application, or just any questions about the MANUELA project that you might have, There is also a help desk available, and you see the email to the help desk there. So please switch.
Yeah.
Your application will be evaluated for 3 criteria. The level of innovation and your concept is one. You have to describe a little bit about your market potential for your application. That will also be an evaluation point. And then how well you have thought through the implementation of your use case. So please, next slide. The schedule for the open call is that it is actually already open. It has been open since the 1st of December last year. We have 2 cutoff dates for applications. The first cutoff date is end of March this year. And then we will select 5 use cases for implementation. And in end of September this year, we will select the remaining 5 use cases for implementation. So if you apply and you're one of the winners for any of these cutoffs, you will be notified directly by Chalmers Industriteknik, and we will start to plan the implementation together with you. And in the project, we have a schedule that the 1st of June next year, all the use cases should be processed and closed. But we have also thinking about extending the period for the project, so you might be able to end your use case after 1st of June next year, but that is not decided yet. So please switch. So when it comes to the implementation of your use case, you will work together with Chalmers Industriteknik. We will project manage the use case for you. We will make sure that it is implemented correctly in the project with all the partners. We will develop the requirement specification together with you. We will also develop flow charts. We will allocate all the resources that is needed. We will agree on the budget, and we will be your contact point in the project. We use a planning tool that we call Project Place, which is rather simple to use. So please. Okay, so that was it about the open call. If you have any questions, you are free to put them anytime. If you're interested in the open call, maybe you don't know exactly how to handle it, you just get in touch with me or with Carolina and we will help you. So these are the contact data.
Yeah.
Thank you.
Thank you, Paul. Thank you. So this was the official part, I wanted to say, the presentation part done right now, and we are good in time. So we have still, well, at least half an hour for discussion or questions or comments from anybody, pretty much. Thank you all the presenters. Okay. Is there anybody who has some wonderings, questions, comments? Don't be shy. Do we have anybody from the companies that you think this may sound interesting to you? I cannot see participant list, but I can stop sharing maybe my screen.
Hello.
Hi.
Hi. This is Robert and Carl from Ultra Scooters. And thank you for good presentations, very inspiring. We have a question regarding the applications and what type of companies you work with, and can we get some more information, like what is the requirements, how long does a company needs to be, how big, and so on?
Yeah, we don't have any limits to that. Actually, we turn Mostly to SMEs and of course also to startups. So if you are an SME and a startup, you're most welcome. This is actually one of the target groups for Horizon 2020 to support SMEs and startups.
Cool.
Mm-hmm.
Thank you.
So if you have an idea, just be in touch with your questions or your application.
Yeah, we will send in.
Thank you.
Great.
Great.
Thank you. Anybody else? Some other questions or comments? Any comments from the presenters?
No,
You talked a lot.
we are looking forward to receiving applications.
Yeah.
Yeah.
And I would like to mention, if you contact Paul and you want to go in some kind of technical details about different things, of course, I talk myself, this is Lars here, I think everyone can be supported behind the interaction where needed, right? Yeah.
Mm.
So yeah, because I think it's good from the beginning to have an idea about how and when and capabilities, so we understand this. We can be helpful there also. This is just, but Paul knows that, right? Yeah. So it's a Carolina, you know that we are there behind you, right? Yeah. Yeah.
Yeah, definitely. And also, I just want to add one thing, that this recording and the presentation, I will make a PDF since it's a huge file and send it to all of you as well who participate today. So you'll get the all the contact information, but also all the pages from the presentations. Yeah.
Perfect, Carolina.
Yes. So do we have anybody else? We still have some minutes left. If there is anybody else who would like to ask anything or use the time since we are here. No, nothing more.
Hi, Carolina.
All right. Well, then, thank you very much, everybody, for your participation, your time, for the presentations, and we'll be in touch then.
Right.
Have a good day, everybody.
You too. Thank you very much.
Thank you. Bye. Bye-bye. Bye.